we're going to build off of the fundamental accounting rule. We have this famous problem, the traveling salesman problem, famous problem in computer science, also in statistics. Suppose that a salesman needs to travel to 10 different US cities to meet with clients. So we're thinking maybe the kind of old days salesman, the 1950s, 60s, something like that, where they actually had to travel, fly or drive to different cities to meet with clients. And the salesman would like to choose the best itinerary for his needs and in some context, maybe the lowest cost or the shortest travel time, something like that. So the salesman would like to take each possible itinerary, review it, see what the cost would be, and then pick the one with the lowest cost. How many itineraries does the salesman have to review in order to find the best one? So what do we have? We have 10 cities and we have 10 slots. So he has 10 slots on his itinerary, and these could be filled in with 10 cities, right? Maybe LA, New York, Pittsburgh, Cleveland, Wheeling, etc. But note a couple of things. Note that number one, the itineraries are such that order matters. So in other words, flying from New York to LA to Cleveland to Portland to whatever, Wheeling to Seattle, we would consider that a very different itinerary than saying, whatever, Pittsburgh, New York, Wheeling, Cleveland, Seattle, LA, right? We think that would probably be a much more efficient one. So the order definitely matters here. So different orderings represent different itineraries. But also note that unlike the previous couple examples, here we're choosing without replacement. If we choose to travel to LA for our first stop, we're not going to travel there again on our 7th stop. We've already visited that client. So I have 10 ways to assign a city to my first slot here. But once I've assigned a city, once I say put LA in my first slot, I can't use it again for the second slot. So then the second slot has 9 cities remaining that can be chosen for the second slot. If I put LA in the first slot and Wheeling in the second slot, I can't choose either of those for the third slot. I have 8 remaining for the third slot, and so on. Down to 3 for the third to last slot, 2 for the second to last slot. In the last slot, I've already used up 9 of my 10 cities. There's only 1 left that just gets 1 choice for that last slot. So I see my number of itineraries. My number of itineraries is 10 times 9 times 8, all the way down to 3 times 2 times 1. And this is about 3.6 million. So probably not feasible for our salesmen, especially in the 1950s or so, to evaluate each one of these to see their cost and then to pick the one with the lowest cost. Our salesmen would have to use some kind of heuristic, maybe come up with a few different decent candidate routes, and then actually evaluate those. So for just 10 cities, there's 3.6 million different itineraries. But this number grows incredibly fast. If we had 11 cities, then it would be 11 times this amount. So we'd be up to 33 or maybe 40 or so million, something like that. This number grows very, very fast. Imagine something like FedEx, who has to figure out how to deliver, I don't know, say 10,000 packages or something, or maybe even more than that, to folks in Pittsburgh every day. Right. I mean, there's an enormous number of different possible itineraries for something like that. They're going to have to use a lot of heuristics and a lot of good computer science and logistics to figure out good routing for all of those packages. So we might notice that we could type in 10 times 9 times 8 and so on into the calculator, but that's pretty tedious. And certainly if we had 30 cities, we really wouldn't want to type these all in. So we have an operator called the factorial operator that does this for us. So 10 times 9 times 8 times 7 and so on. If we have a positive integer and we take the factorial of that integer. So if we compute 10 factorial, that's the product of that positive integer with all other positive integers less than it. Our calculator has this built into it. So in the math menu over here, the top left is second and then alpha and then math. If we go to the math menu, we notice across the top there are 4 submenus: math, number, complex, and probability. We're going to go over to the probability submenu. And then we note line 4 here. We're going to navigate down to line 4. That's our factorial operator. If we hit enter, it puts a factorial in for us, and it has this answer there, but that's just because I hadn't typed anything in. So if I want to compute 10 factorial, I type in 10, and then I navigate to that factorial operator, math, go to the right to the probability menu, go down to the factorial operator, then hit enter. We have 10 factorial entered. Now we can hit enter again, and that's our 3.6 million answer that we had before. Something kind of interesting to note, it's a very helpful property of factorials, is that 10 factorial, if I pop this 10 off the front, then what am I left with? I'm left with 9 multiplied by all other positive integers less than 9. So I could think of this as 10 times 9 factorial. Or I could do that again. This is, 10 times 9 times 8 factorial. I can pop some of these leading factors off of a factorial, and I'm still left with something that can be nicely concatenated under a factorial. So this is a recursive idea. Those of you who have taken programming and things before, you might have actually programmed a factorial function as a recursion. Now something, so we can say as a general rule, n factorial equals n times n minus 1 factorial for n a positive integer. But then to define this recursion properly, we need a base case. And you might say, well, let's just take 1 factorial equals 1 and make this a positive integer bigger than or equal to 2. I suppose we could do that. We're actually going to see it's going to be much nicer to actually define 0 factorial to be 1. This might seem like a very strange thing when I said the idea of a factorial is to take a positive integer, multiply by all other positive integers less than it. But there's a couple perspectives in which this makes sense. One is that some of our future rules will just we'll be able to avoid a bunch of special cases by allowing 0 factorial equals 1. That actually kind of even makes sense in our factorial rule. If our salesman had 0 cities to visit, well, how many itineraries are there to just, sit on your couch and not go anywhere? Well, there's, I guess, only one, right? You just have to not go anywhere. So in that sense, the 0 factorial equals 1 kind of makes sense. There's also a deeper reason why this makes sense, and it's related to something called the gamma function. We're not really going to get into that, but there is a somewhat deeper reason why 0 factorial equals 1, does also make sense. And this is just a little exercise like I kind of did up here, where we could break apart our factorials. We could break our factorial using the recursion down into the other definition. So the general factorial rule is when we have n distinct items to be allocated to n slots, where order matters, in other words, where a different ordering represents a different outcome, then the number of unique outcomes is n factorial. So another example, reshufflings of a deck of cards. So consider a standard deck of 52 cards. And we want to reshuffle, we want to shuffle them very well, right? So like think of like throwing them up in the air, they go everywhere and then collect them back together, very nicely shuffled. How many such reshufflings are there? Well, we can think of there being 52 slots. I have 52 ways to assign a card to the first slot. Each of the cards is unique. 51 for the next, 50 for the next, so on to 3 times 2 times 1. So there are 52 factorial different reshufflings. How many is that? Let's check. So I could do 52 and then factorial. I want to go math. I could go all the way to the right to get to the probability menu. I could also just go left 1 and then wraps around. So I'll do that. And I could navigate down to 4 and hit enter, or I could just hit the button 4. If you want to do it the long way, no problem. But you can just go left 4. That will also enter a factorial. It's a little quicker. And I see that I have this kind of strange result. I have 8 point something, E67. That E means times 10 to the power. So this is 8 times 10 to the power 67. Again, this is an enormous number. The physicists estimate that there are something like 10 to the 80th particles, like electrons and things in the entire universe. So you can imagine 10 to the 67 is getting up to about that size. And I kind of did the math on this one time a while ago. And if you imagine that something like every person who has ever lived in history or is currently alive, if they all lived 100 years and they all did nothing their whole life but reshuffle cards, and they could reshuffle it like 1 shuffling per second. I forget if I did per second or per minute or something like that, but like the chance of any 2 people ever having at some point gotten the same shuffling of cards is like absurdly small. So I mean, this is an extraordinarily large number of reshufflings of a deck of cards. Now you will hear every once in a while there will be a group of people playing bridge or something and some really crazy thing happens where I don't know, like they deal the cards to the 4 people and like each of the 4 people only gets like a single suit, like one person gets only clubs and the other person gets only spades or something. Most of the time, if you actually dig into what happened, I mean, some people I suppose could just be lying to get in the news or something, but most of the time you can kind of make sense of it by saying, okay, well, when people actually shuffle cards, we might start with a new deck, which has obviously a non-random ordering. It has the random ordering of basically every new deck out there. And then we shuffle them, but, we kind of think that by shuffling them, we're randomizing them, but really, if we do a riffle shuffle, we tend to kind of roughly kind of interleave one from the left, one from the right. And then every once in a while that gets jumbled up a little bit. So it's maybe, 1 or 2 shufflings doesn't randomize the deck as much as we might think. And so it's more likely that those kind of situations happen from starting from a new deck, the predictable nature of how people shuffle, and then that led to something that seemed very unlikely to happen, but you could easily explain it away with starting from a new deck and then human behavior. But if somebody had picked up a deck of cards that they had used 20 times already in different games and then done this, that would be much more impressive. Or if they had riffle shuffled them, say 8 or 10 times, at that point they're pretty well randomized, and that would be much more impressive if something like that were to happen in a situation like that. So again, revisiting the traveling salesman, as I mentioned, the traveling salesman has 10 factorial different itineraries to look through. As kind of a side note, n factorial kind of looks like n to the power n. It grows faster than even an exponential function. So we have an n in the exponent, but also an n in the base. So this grows extremely fast. It grows faster than an exponential function. There aren't a lot of things that grow as fast or faster than factorials. So if we even went up to say 20 factorial, if our salesman will do second enter to bring up the previous entry, and then if our salesman had 20 cities to visit instead, all of a sudden, instead of 3.6 million itineraries, he's got 2 times 10 to the 18th itineraries. As an aside, if we do on the calculator 69 factorial, we see that we get about 10 to the 98th. And if we try to do 70 factorial, we get an overflow error. 70 factorial is too big for our calculator to do, or any other input bigger than 70. At least for the TI-83. Now this could change depending on what calculator you have. Some more modern calculators might be able to do higher numbers factorial. But for the 83, 69 factorial is the highest factorial that it can do without overflowing. This actually becomes a bit of an important point later on. We'll see that in some more complex situations, we have a lot of cancellation in the numerator and denominator. If we try to explicitly write out a formula with factorials, the calculator might try to calculate it one way and overflow, but maybe if we enter it in the calculator a slightly different way, the calculator can take advantage of that massive cancellation and not overflow. So this will be an important point later on, that factorials grow very quickly, and inputting large number factorial into the calculator can easily make it overflow. Okay, so let's consider a lazy traveling salesman. So this salesman also was told by his boss to go to 10 different cities and meet with 10 different clients. But he's going to only travel to 6 of these cities and whatever, spend the rest of the time on a beach in Florida or something. How many itineraries does this salesman have to choose from? So this salesman has 6 slots to fill in rather than 10. But he still has 10 different cities to choose from. So still 10 different cities could take up the first slot, then 9, 8, 7, 6, 5. So I see the number of itineraries is 10 times 9 times 8 times 7 times 6 times 5. And again, I guess I could type this into the calculator, but we could imagine, having 30 cities to visit and picking from 15 of them. And we wouldn't want to type that in. So let's try to come up with a formula that we can write a little more concisely. Something that I noticed here is 10, 9, 8, 7, 6, 5. Like, this is a start of a factorial. If only I had a few extra factors, it would kind of complete the factorial. This feels to me like completing the square from algebra. So this would be super nice if it was this instead of stopping at 5, because then I could just write 10 factorial. Now I can put these factors in here. That's not a problem as long as I take them out. But nicely enough, on the bottom, I just end up with 4 times all of the other positive integers less than it. In other words, I end up with 4 factorial on the bottom. So if I did 10 factorial divided by 4 factorial, I get 151,200. I could also have done 10 times, wrong screen. There we go. I could have done 10 times 9 times 8 times 7 times 6 times 5. That would give me the same answer. Now, it turns out this kind of structure comes up enough that we have a name for it. We call it a permutation. And we have a formula for it. I note that the 4 factorial on the bottom is related to the 10 cities, the 10 items I have to allocate, versus the 6 slots. It's 10 minus 6 factorial. So 10 factorial over 10 minus 6 factorial. We give that the name 10p6. And we would just say it that way, 10p6. If we go into our math menu, go to the probability menu, we note this NPR operator here in line 2. This NPR operator is a binary operator. It's kind of like a plus or a minus. So if I wanted to add two numbers, I would write like 4 plus 3 and get 7. So I would enter number, then operator, then number. NPR works the same way, the permutation operator. So if I wanted to compute 10p6, I would type in 10, the first number that I'm interested in. Then I would go to my math menu, probability, and option 2 here, NPR. I would insert that operator. It's acting kind of like a plus sign or something like that between two numbers. And then I would enter 6. And I see again, I get 151,200. So something that's a little funny is we like actually completed the factorial here to get a formula like this. But if I imagined, say having 100 cities I could visit, or the salesman could visit, and he's only going to choose 6 of them. What's 100 P6? So insert a 0 here. 100 P6, I mean, it's a big number, 8 times 10 to the 11, but it's not, it doesn't overflow the calculator. But what would 100 P6 give me here? This would give me 100 factorial over 94 factorial. If I were to try to do that, if I were to try to do 100, oh, keep forgetting to switch to my calculator. If I were to do 100 factorial divided by, what is it, 94 factorial. Now I know that there's going to be a ton of cancellation here between the numerator and denominator, and that's going to keep the size of the overall answer to a number that's not going to overflow the calculator. But if I try to do this, the calculator overflows. Why is that? Well, because the calculator strategy when I type these things in this way is to say first calculate 100 factorial, then calculate 94 factorial, then divide them. But since I have a huge number over a huge number, it just overflows when it first tries to calculate 100 factorial. The calculator is not quite smart enough to know that, okay, there's going to be a lot of cancellation. I should like do the cancellation first and then see what I get from there. But the programming for the permutation operator, that 100p6 works just fine because that does take into account that cancellation. So the permutation operator will be coded in just as kind of a loop that would multiply over 10, 9, 8, 7, 6, 5, and it would avoid those factorials growing too large. So if you're going through a problem and you're getting calculator overflows, ask yourself, okay, am I putting in big factorial numbers? And can I rethink that in terms of, say, a permutation operator, or maybe what we'll see later, a combination operator? So the permutation rule, when we have n distinct items to be allocated to R, a number less than n slots, where order matters, the number of unique outcomes is NPR equals n factorial over n minus R factorial. So that's the permutation rule. Now, quick question on this. What if, so NPR is n factorial over n minus R factorial. What if R equals n? So what is NPN? Well, that's n factorial over n minus n factorial. That's n factorial over 0 factorial. So keep in mind up here, I defined 0 factorial to be 1. So this just makes this n factorial. Is this reasonable? Well, yeah, I think it is, right? If we have n items to be allocated to n slots, that's just the regular salesman problem, right? The regular traveling salesman problem. That's just our factorial rule. So we actually see that our factorial rule is a special case of the permutation rule where just r equals n, or the permutation rule is a generalization of the factorial rule where we have fewer slots than number of items. And we can really just kind of wrap the factorial rule into the permutation rule if we wanted to. We could just say allocate it to r less than or equal to n slots. And then the factorial rule just kind of becomes part of the permutation rule, just as a special case of it. Okay, so now let's look at a lazy salesman, but now we're in the modern era where all our meetings are over Zoom and such. So now we have a lazy online salesman, a lazy remote salesman. Now this salesman is supposed to meet with 10 different clients. They're only going to meet with 6 of them. But they don't really care about order, right? So if they meet with the client in LA, first, and then in New York second, and then Seattle third, that's no more wasteful or worse than, going LA, Seattle, New York, right? There's really no efficiency or inefficiency to be had with different orderings of different sequences of clients. So I'm going to call these agendas instead of itineraries, suggesting that the order doesn't matter. It's just a question of which clients am I meeting with today. It doesn't really matter which one I meet with first, second, third, because we're remote. So if I have 10 items, 6 slots, order does not matter. How many agendas do I have? Well, one thing I might do is I might just start by saying, well, what if order did matter? Right, I have my 6 slots. Well, if order did matter, my number of agendas would just be 10p6, right? It would just be 10 factorial over 10 minus 6 factorial. But now I say, okay, well, but I want to impose the condition now that order does not matter. What does that do? Well, I could imagine picking an agenda like LA, Cleveland, New York, Seattle, Miami, Wheeling. That might be one itinerary that would be a distinct itinerary under the order matters, under the permutations structure. But if I had, for instance, Cleveland, LA, New York, Seattle, Miami, Wheeling, that would be a different one under the permutation structure. Or LA, New York, Cleveland, Seattle, Miami, Wheeling. Right. In other words, there's going to be a bunch of different itineraries that when we impose order does not matter, count as the same agenda. So these are different itineraries. But these ought to be the same agenda. In other words, when I counted up here, 10 factorial over 10 minus 6 factorial, I've overcounted. By how much have I overcounted? I would like to find out how much I've overcounted by and then correct for that. Well, I've overcounted by a factor of the number of different itineraries that I want to wrap under the same agenda. if I look at an itinerary, in this case, I have 6 cities put into 6 slots. How many rearrangements, how many permutations of 6 cities into 6 slots are there that I want to count as the same agenda? Well, I could have put any of these 6 cities in the first slot. I could have put any of the remaining 5, 4, 3, 2, 1 in the next slots. Well, I've overcounted by a factor of 6 factorial. 6 factorial is the number of ways to put these 6 cities into these 6 slots. That's just the factorial rule. So if I leave this formula alone, I get the wrong answer because I've overcounted by a factor of 6 factorial. So I just correct. I divide by 6 factorial. Right? That corrects for the overcounting that I did initially. That respects the fact that there's lots of itineraries from the initial counting that are the same agenda. In fact, for each agenda, there are 6 factorial different itineraries that now map to that single agenda. So I just divide my previous kind of first pass answer by 6 factorial to correct for that. So this structure also has a name. This 10 factorial over 10 minus 6 factorial times 6 factorial is called a combination. Combination. And we say 10C6, or sometimes the C is pronounced choose. So sometimes we would say 10 choose 6, or we might say 10C6. And we can come back over to our calculator to calculate this. 10C6 works just like 10P6. So just like above, we would type 10, and then we go to our math probability menu. But here we go to the third line, NCR combinations. And I see that 10C6 is 210. Right, much smaller number than the, what was it, 151,000 or so that we had up here. Only 210 different agendas for the lazy online salesman. Because there are 6 factorial, that in and of itself is a pretty big number. What is that, 720, something like that? That's a pretty big number of distinct itineraries that map to a single agenda. So that's why our result here is so much smaller than when order mattered. Something else that we might note is that if I had, say, 10C4, well, that's 10 factorial over 10 minus 4 factorial times 4 factorial. But I note that 10C4 should just be the same as 10C6. There's a symmetry here, right? That 4 there and that 4 there. Or that 6 there and that 6 there. So what's another way to think about these combination of permutation rules? Another way to think about combinations is, well, when I say I want to take 10 items and put them into 6 slots, but order does not matter, I can kind of imagine that I have a bag of 10 items. So I have a bag of 10 pieces of paper, each one has a different city written on it. And I want to pick 6 of them out. Remember, order doesn't matter. So I'm just picking 6 to put into these slots. And then I'm going to leave the remaining ones in this bag also unordered. I could really think of these slots just as like another bag, right? Or maybe I'll use the analogy of a box. So I could really think just putting these 6 into another box where order also doesn't matter. So how many ways are there to pull 6 items out of this bag and put them into another box? In other words, that's just asking how many ways are there to split these 10 items into an unordered group of 6 and an unordered group of 4. Well, that's the same way that we can split it into an unordered group of 4 and an unordered group of 6. So likewise, 10 choose 1 and 10 choose 9 are the same number, or 10 choose 2 and 10 choose 8 are the same number, because they're really asking the same question. How many ways are there to split 10 items into an unordered group of 1 versus an unordered group of 9, or 2 versus 8? Does that mean permutations are share the same symmetry? Well, the answer is no for permutations. We can see that in the formula, but we can also see this kind of practically, that if we have our bag of 10 items up here, and if I pick out 6 of them, well, now it is important that we put them into slots, because the 6 that we pick out, we have to decide which one is going to go first, which one is going to go second, which one is going to go third, fourth, fifth, and sixth. The other 4 are just going to be left unordered in the bag. So the ones that we pick out, we impose an ordering. The ones we leave in the bag, we leave unordered. So we're partitioning these 10 into 6 ordered versus 4 unordered. That's different than having 4 ordered versus 6 unordered, right? We can't swap those. We lose that symmetry. But for combinations, we have this nice symmetry, and we can take advantage of that in some problems in the future. The other thing to note is something like 10 choose 0 is 10 factorial over 10 minus 0 factorial times 0 factorial. This ends up being 10 factorial over 10 factorial times 1, or just 1. If I have a bag of 10 items, how many ways are there to pick out 0 of them? Well, I just leave them all in the bag. That's the only way. And likewise, 10 choose 10. This becomes my 0 factorial. 10 factorial over 10 factorial is 1. If I have 10 items in a bag, and how many ways are there to pick all of them out of the bag and put them all in the box? There's only one. I just have to pick them all out, put them all in the box. So the combination rule says when we have n distinct items to be allocated to R less than n slots, where order does not matter, number of unique outcomes is given by this formula. And we can have R equal to 0 or R equal to n. And we see that doesn't really cause any problems, right? By defining 0 factorial as 1, we allow for those edge cases, and that works out just as we would expect. So a quick summary, the fundamental counting rule, we are in a structure where order matters, and something that we sometimes say is we're choosing with replacement. In other words, when I was all the way, where was I? When I was up here in my license plates, right, I had A through Z items that could go in the first slot. If I pick A for the first slot, it's not like I can't use A in the second or third slot. I replace A back into the pool, and I could choose A again. Unlike, say, the traveling salesman, where if I go to LA for the first leg of the trip, I'm not going to go back to LA. Once I've used that, it's gone. I can't reuse it. So the fundamental counting rule, order matters, choosing with replacement. The rest are choosing without replacement, factorial, permutations, and combinations. Remember that factorial rule and permutations really are kind of the same rule. Factorial is just a special case of the permutations rule, or permutations is a generalization of the factorial rule. The factorial and permutations share that order matters, and we're taking without replacement. But the factorial rule has the little criterion that we have the same number of slots and items. which makes the permutations rule a generalization of factorial rule. And combinations, the big difference is that order does not matter with combinations. Still choosing without replacement, but order does not matter.